Okay, thank you. So I'm Stanley Bach. I'm from the University of Illinois. I'm a PhD student there. I'll be presenting work that my research group has done over the last couple of years, specifically dealing with some of the problems we saw in the previous talks. So actually it was a very good morning, and we saw a very good motivation as to some of the problems that can occur when you try to use commercial off-the-shelf components to do real-time computation. So my motivation is similar to the one in the previous talk. They had a chart there showing, for example, the lines of code over time in different systems. So the lines of code, you noticed, saw this nice exponential trend. We have a 10,000-fold increase, I think it was, in the number of lines of code over 30 years. The capabilities we're putting into modern real-time systems also is increasing. So not only is the lines of code, also the computation demands, the I/O demands, they're all following the similar trend. What we don't want is an associated exponential increase in the cost of the system. So one way to address this is continue to use these commercial off-the-shelf components, which are also having these exponential gains in performance that can match the demands and capabilities that we're giving them. So my talk is divided into 3 parts. So in the first part, I'll talk about the benefits and challenges dealing with COTS systems, specifically in the real-time domain. And there's 2 solutions for 2 specific problems that I'll mention. The first is a COTS-based I/O management system, so that's dealing with unpredictability that comes from the input-output system in a COTS system. The second one is the predictable execution model. So whereas the one before dealt with the I/O system, the predictable execution model deals with the computation occurring on the cores themselves. So why would we want to use COTS? The benefits are there's a lower cost associated with using off-the-shelf components. They've already been built and mass-produced, so the manufacturers can lower the cost for this reason. The target market you saw was 80% for cell phones and personal computing and game devices, and only a small 2% portion for safety critical systems. So through mass production, they can have lower costs. You can also lower your system development time by using off-the-shelf components. And the reason for this is that your component it's already been manufactured, so you can immediately start using it, rather than going through the entire design process where you have to design your component, test the hardware, debug it, and then you're able to use it. And this is pretty significant in our domain, in the aerospace domain, because if you look at some of the systems that get deployed, from the time that they're initially conceived of to the time that they're deployed, and you look at the hardware that they're being used, you might have something like 5 or 10-year-old hardware that's being used on these systems. Whereas the industry has revolutions in the performance and power properties of the systems that they have basically every 2 years or so. So by having newer hardware, we can take advantage of these developments. COTS components also typically have standardized interfaces. So this is helpful because a large part of the development time for modern system deals with system integration time. So after you design all your components in isolation, you try to put them together, and for whatever reason it doesn't work, or you have to change some of these components. By using standardized interfaces, you can help that process along. And then finally, the main motivator is, again, you have better performance in these types of systems. So you want to have this exponential increase in capabilities. By having better performance with COTS, we can basically allow us to have these additional capabilities. So just as an example of the better performance, if you consider 2 specific buses. So there's the custom-made Safe Bus by Boeing, which runs at 60 megabits per second. And if you compare that to an off-the-shelf PCIe bus, which runs at 16 gigabytes per second, you see that there's a 3 orders of magnitude difference in this performance. So that's just one example of how COTS components have better performance. The downside of using COTS, as we saw in the previous talk, was that COTS components are typically designed to optimize for average case performance rather than worst case performance, rather than for things like predictability and reliability that we want in our systems. So this is a typical COTS system right here. you'll notice that there's a CPU which accesses some shared main memory through a north bridge. Then you'll have a set of peripherals that are all also accessing RAM potentially, and these go through a series of buses as well as bridges, and the specific configuration depends on the specific architecture you're targeting. But any of these shared components, such as main memory, such as these shared buses, these shared bridges, is a source of unpredictability. Because for a COTS system, these shared components aren't designed with real time in mind. The low-level arbiters are not necessarily real time. So the first problem that I'm going to look at is I/O bus contention. So just dealing with the I/O subsystem, where you have different peripherals accessing this shared main memory, there's a lot of sources of potential conflict. So again, these shared buses that can be concurrently accessed by these systems, if they're DMA-enabled peripherals, this means that completely separate from the CPU, these cores can initiate access to main memory. So it's very possible that they'll access main memory at the exact same time. It's possible that they'll be able to do that, and then you'll run into these problems. The downside of this is that your associated increase in communication delay depends on the low-level arbiter. So consider an example here on the right, where we have two DMA-enabled peripherals, and they're transmitting at full speed on something like, let's say, PCIX bus. A very sort of sensible arbitration policy that may be used is something like round robin. Unfortunately, when you use round robin, you don't have latency guarantees unless you know the size of your low-level transactions. So for example, consider a case where one device might be transmitting 1 byte at a time, and the other one is transmitting 10 bytes at a time, and they're both trying to saturate the bus. If you're doing round robin, one of them is going to get 10 times as much bandwidth as the other one. So as a system designer, if you want to do an analysis on this type of system, you have to know what these low-level transactions look like. And this can have an effect, of course, on the execution time. So, or in this case, the transfer time. So in this case, we have one peripheral here, which has a period of 8. So it's going to try to transmit 2 times within 16 time units. And then this peripheral has a period of 16. So it's only going to try and transmit this one block in this period of 16 time units. If you have no bus sharing, this one takes up 3 time units of access on the bus. And this component takes up 6 access, 6 units of time. If you have bus contention and you have 50% bus sharing, everything is still okay, because this transaction length increases to 6, but it's still in time to meet the real-time communication deadline. If your bus contention is different, like 33%, 66%, which it could be, now you run into a problem where this communication flow basically doesn't finish in time for the next period. So in this case, maybe most of the time when you run the system, you don't run into a miss on the deadline, but then in some certain circumstances, if the bus contention goes the right way, you might miss a real-time deadline. So that's a problem for analysis. And so here's just an experiment we did to validate this. So actually, I'll come back to this one later on when we talk about our solution, but basically we just took 4 PCIe peripherals and we made them send periodic traffic on the PCIe bus. And so this is actually a trace that we measured, where normally this component has a very short transfer time, but when all the components start to transmit at once, when we have this sort of critical instant, this transfer time is increased to the point where you can have a missed deadline. The second problem that I'm going to address is memory contention. And this is memory contention between the peripherals and the CPU. So the CPU and the peripherals can concurrently send accesses to main memory, and once you have a shared resource, then you have a potential bottleneck in the system. And so for this type of problem, you have the same situation where, again, the low-level arbiter is probably not designed with real-time in mind. In some cases, it's even unknown. So if there's an on-chip bridge that communicates with main memory, it's very difficult to get those details from a manufacturer. So you're sort of stuck here in that even if you want to do some sort of analysis of the worst case performance, you actually don't know the low-level details of this type of system. This is very problematic in that the CPU activity can be stalled due to this memory contention. So you might measure your worst case execution time, even taking into account that you'll have cache misses and you have to go to main memory. But then when you integrate the system, and now you have these flows coming from the peripherals, and you look at your worst case execution time, it can increase. So how much can it increase by? Well, it depends on the components that are concurrently accessing main memory. So this is also a problem, by the way, if you have a multi-core system, in that multiple cores can concurrently try to access main memory as well. But the experiment that I'll show here is basically just considering a single core system and then a single peripheral. So what we did is we took an Intel platform and we created a PCIX peripheral that would basically generate various amounts of traffic with various transaction lengths. And then we would have a task which continuously suffered cache misses so that there would be now competition for main memory. And so what we looked at is we tried to measure then what was the increase in worst case execution time due to this single peripheral running. And so it's a function of both the percent of throughput of the PCIX bus, basically how much traffic is being generated, and this is the transaction length. And this is the increment in worst case execution time. So these values aren't 0. These are actually values that we couldn't actually produce that much traffic with that bus size. But basically what you see is as you increase as you saturate the bus more and you have a larger transaction length, you can have up to a measured 44% increase in worst case execution time. We've also done simulations on this for multi-core systems where you can see sort of a linear trend where as you keep adding more cores to the system, your contention can grow linearly, and therefore your worst case execution time can also grow linearly, which is sort of what we want to avoid. The reason we're adding more cores is because we want to have more computation power. We don't want to have less. So to integrate COTS within a real-time system, I presented these two problems. And so the next two sections of the talk are about two solutions for these two problems. For the I/O flow interference problem, we're going to propose a COTS-based I/O management system. To address the memory contention problem, we're going to propose something called the predictable execution model for real-time tasks, or PREM. And so the key idea of both of these methods, which maybe the key idea of the talk, is that when you have these shared resources that you don't know what these low-level arbiters are doing, you can still use them in a real-time system as long as you resolve the contention at a higher level. So this will mean that if you schedule the requests for these shared resources such that two requests never occur at the same time, it doesn't matter what the low-level arbiter is as long as it's a work-conserving arbiter, I guess, as long as if there's one request, it actually grants it. So by doing scheduling at a higher level, we can still do real-time on these non-real-time platforms. So problem one that I mentioned before was I/O bus contention. And so this was contention at the level of basically the peripherals would autonomously transfer data to main memory. And then contention would occur along the shared buses, the shared bridges, and the shared access to main memory. And so we had mentioned before that if we have round-robin arbitration, we don't have timeliness guarantees for these types of real-time flows. So what we propose is actually a modified system architecture. So we're not modifying the COTS peripherals, and we're not modifying the COTS motherboard, the bridges, or the buses. What we're doing is we're interposing another element between the COTS peripheral and the COTS motherboard. And so these interposed elements are called real-time bridges. Additionally, we have something called a peripheral scheduler, which is connected to each of these real-time bridges. And so these two components together will be able to provide this sort of implicit high-level scheduling that will resolve the conflicts before they access these low-level arbiters. So let's go into details a little bit about these components. So the peripheral scheduler, which again is this component right here, accesses each of the real-time bridges. And so what its job is to ensure that only one real-time bridge communicates at a time, accesses the bus at a time. And so what we did is the interface between the peripheral scheduler and each real-time bridge is actually a pair of wires. One wire which indicates that data is ready, which the real-time bridge will send to the peripheral scheduler, and then the peripheral scheduler will in turn send a block signal back, which will tell it when it should block, when it should unblock. So for the scheduling, the scheduling in this type of system, we can we have lots of options available to us. The simplest one is if we want to do something like fixed priority scheduling. That's actually very simple to implement in hardware. For example, the highest priority task can basically be unblocked whenever its data is ready. The second highest priority task can be unblocked whenever its data is ready and the highest priority task is not transmitting. So this is very simple hardware that you could do to run fixed priority. We also have different options here other than just simple rate monotonic scheduling. So one thing that we actually implemented was a sporadic server policy. So that's a traditional scheduling algorithm from real-time systems theory for CPU scheduling. And we were able to do this to do basically bus scheduling on the bus itself. So the peripheral scheduler is communicating to each of the real-time bridges, and it resolves the contention at the higher level. So you have basically a situation like this before, where now the lower priority peripheral will be blocked for a certain amount of time while the higher priority peripheral transmits. And so now it doesn't really matter what the low-level arbiter is doing. You always get complete access to the bus, contention-free access to the bus when it's your turn to schedule. And so in this way, we can resolve the problem. So the other component that we created was this the real-time bridges itself. So let's take a closer look at that. So this is a little bit more complicated component than the peripheral scheduler. This is actually a complete system-on-chip design that we made. And so it's interposed between, this is the controlled peripheral, and then this is the rest of the system itself. So you notice there's two PCI interfaces, and then this controlled peripheral acts as if this is the system itself. So it'll transmit data to local RAM residing on the real-time bridge. And then when it'll indicate that data is ready to the peripheral scheduler. The peripheral scheduler will in turn unblock this peripheral, and then it'll end up transmitting data from local RAM to main memory. So there's some amount of sort of hardware effort that we did to develop this, but this can be generalized again for a type of interface, so we can make this general for a PCI interface. The software effort, however, once you have the hardware, you do have to modify the driver slightly to take this into account. So if you're using an off-the-shelf peripheral, you probably have an off-the-shelf driver, for example, an open source Linux driver that you could use for this type of system. Usually these drivers are written such that there's a low-level driver part, which is in charge of interacting with the hardware, and then there's a high-level driver, which basically takes the data and sends it to the, basically like if it's a network interface card, it'll send it through the networking stack and eventually to the user application. So a well-written driver may be written in a way that's this distinction is clear. And so what you have to do is you have to split this driver. So you put the low-level driver on the FPGA such that it can interact with the controlled peripheral and get the data in RAM. But then the FPGA won't process this data. Instead, there's a code written which transfers the data from local RAM to main memory, and then the high-level driver will stay on the host CPU. In that case, the sort of application that's running on the host CPU doesn't even know that the real-time bridge exists. So it just thinks it's a regular network card. It doesn't realize you're doing real-time scheduling on the bus. So we implemented a prototype. And so we actually considered an Ethernet card for our off-the-shelf peripheral. And so we had an optimized implementation, which basically allowed us to do no extra software copying. So basically the data went from the peripheral to the FPGA RAM, and then was copied directly to the host DRAM. So there wasn't any extra software copying there. And we were actually able to use user applications in an unmodified way using this real-time bridge. So back to this sort of experiment which I had shown earlier in the presentation where, again, we had 4 PCIe peripherals. And due to the contention at the critical instant, we had a deadline miss. These are the actual parameters that we used for this experiment. So when the flows weren't aligned, tasks could meet their real-time deadline. But again, if everything's executing at once, you use a low-level arbiter and you miss your flow deadline. So with our peripheral scheduler enabled, we can now prioritize traffic on the network. So this is, again, a trace that we measured from an actual system. It's not a simulation. And so near the critical instant where all the tasks are almost released at the same time, you see that now we can block actually the peripherals from transmitting in such a way that every task meets its real-time deadline. And so we actually used, again, a sporadic server to do this, and here's the server period and budget. And using sporadic server scheduling theory, you can say that this system is schedulable, and then actually when you implement it, you see that it's also schedulable. So the second part of the talk deals with the second problem, which is memory contention. Basically, peripherals, when they access main memory, they may compete with different CPU cores that are accessing main memory at the same time. So again, the low-level arbiter in this situation is unknown, and it's not real-time, likely not real-time. So the problem here is that the CPU activity can be stalled due to this memory contention. So if you look at your worst-case computation time, it can be greatly increased due to this low-level contention. So what we propose is actually PREM, which is a predictable execution model for the cores running on the system. So on this slide, I have the rules for PREM in words, and the next slide, I have a picture that helps explain it a little bit better. So what we're proposing is you can't insert a component between each core and main memory to block the core, and you wouldn't want to do that anyway, because then you'd have an increase in the worst-case execution time of the component. So instead, what we propose to do is to modify how execution is performed on the core itself, such that you can then schedule when the core accesses main memory. So in order to do that, we divide real-time jobs into two types of scheduling intervals. So there's compatible intervals, which are backwards compatible. So they're just compiled and run in the traditional way. And then there's some intervals which are called predictable intervals. And these intervals are executed according to, these intervals basically, they're divided into two parts. One is a prefetch phase, where these intervals will access the main memory they access, load it into local cache. And then there's an execution phase, where the task will run on the core, accessing only local cache. It won't be accessing main memory at this time. So another component of the PREM execution model is that we keep the execution time of predictables constant. And so the reason we do this is that during these execution times, when you're not accessing main memory, the peripherals are going to be accessing main memory. So by keeping the execution time constant, we can guarantee bandwidth for the peripherals themselves. And so we also have to control when interrupts are raised to make sure that we don't, for example, raise an interrupt during one of these execution intervals, and then the OS will switch over to a different task and cause it to access main memory. So visually, this is what a predictable interval looks like. So again, some parts of the execution, such as the drivers, are kept backwards compatible, where we don't modify them at all. And then we try to modify some parts of the execution to look something like this, where there'll be a memory phase where the task will try to prefetch all the data that it's going to access during the rest of the interval into the local cache. And then there'll be an execution phase where the task is just doing CPU and cache-based execution. It's not accessing main memory. And then during this time, the peripherals will be transmitting data. And that's, again, why we keep the execution time constant. So this is just a larger example with two tasks and two I/O flows. It's not important to look at all the details, but basically what you can do is, if you look at this interval right here, its I/O task is basically has some guaranteed bandwidth in the previous period where it can, for example, send input data to RAM. Then at its start of its period, it runs a compatible interval. This would be the driver that receives the data from the RAM. Then it executes a predictable interval. Then it produces output data. And this output data is sent to the RAM. And then during the next interval, the output data will be sent back to the output peripheral. So in this case, you have sort of like double buffering in the system, in that when the predictable interval starts, you're guaranteed that the data is in the system. And when the execution phases are executing, that's when the peripherals are actually doing the data transfer for the previous and next intervals. And another thing to note about this trace is that you have this sort of implicit scheduling for the main memory. So only one component is accessing main memory at a time here. So at the first interval, you have the compatible interval, where that's accessing main memory plus the memory phase. Then here you'll have some I/O flow. Then after some time, you have another compatible interval, and the I/O flow is stopped. And if you go through the entire example, you'll see that, yes, only one component is actually accessing main memory at once. So the PREM programming model, we use it with a high programming language like C. And basically, I'll now go through basically what you have to do to make your application compliant with this PREM programming model, where you can do this prefetching and this execution. So we set some programmer guidelines, and then we also use a modified compiler. And so I'll go through these two parts now. So the programmer creates some annotations and he puts them in the code. Currently, right now, this is done manually. And then the modified compiler will then generate code that basically performs the cache prefetching at the beginning of the interval based on the annotations the programmer provided. It'll enforce the constant execution time for the predictable interval to guarantee I/O bandwidth for the I/O flows. And then one more thing it'll do is it'll send co-scheduling messages to the peripheral scheduler. So we had to modify our system-wide peripheral scheduler in the system in such a way that it's now also a component sitting on the bus, and it'll receive messages from the CPU indicating when the CPU enters these various phases. So then the peripheral scheduler will know that now the core is running an execution phase so that it can allow peripheral traffic to occur. The programmer's job is basically to, as a programmer who wanted to apply prem, what you would do is you would profile the code to identify where the program spends most of its execution time. So again, it's not necessary that you change your entire program to make it into these predictable intervals. You only have to do that for the parts where the majority of execution occurs. So after you do that, you have to obviously do some worst case execution time analysis on your code. If you're running in a real-time system, that's something you need to do. You need to identify, this is probably the hardest part, is identifying the memory regions that are accessed during that interval itself. So basically, anytime you access a global data structure, that has to be indicated in these annotations. And then you obviously place the annotations at the beginning and end of the predictable interval. The compiler then will look at these annotations. It'll prefetch the code in the stack for your particular function. It'll prefetch the global memory based on what you indicated in your annotations. And then it'll send the messages it'll add basically the messages that are sent to the peripheral scheduler when your peripherals start and end, as well as indicating how much time you have for your execution phase, so it knows how much time it can schedule the peripherals for. And then it'll provide some it'll add a busy loop to enforce this worst case constant execution time for predictable intervals. So there's some programming constraints basically if you want to use this prem approach. So some of them are you can't have so for linked-based data structures, you have to be sort of careful in how you use them. So if in your predictable interval you use only a small part of a binary tree, for example, but you can't figure out what that part is at the start of your predictable interval, you'll have to be pessimistic. You have to prefetch the entire data structure. So in general, you want to avoid these linked-based data structures. The programmer has to be able to figure out what the accessed memory regions are as well. So this generally is not really a solvable problem, but for practical applications, of course, a programmer can look at it on a case-by-case basis. You can't have system calls right now within our prem implementation. You can't have stack allocation. So this means that you have to know the size of the stack at the start of your predictable interval. There's ways when you're programming in C where you can dynamically change the size of the stack. For a similar reason, you can't have recursive function calls. So if you have unbounded recursion, you don't know how large the stack will grow. And then finally, all this memory that you're prefetching has to fit in a cache in such a way that during the execution interval, you're not going to be accessing main memory. So although there's numerous requirements for using prem, we argue that these aren't really significantly more restrictive than if you're using static analysis to do worst case execution time estimation. So typically for those, again, you won't have things like unbounded recursion, for example. So if you're in a real-time system, although there's these constraints, they might not be overbearing on the system. So we made a prototype for prem. We had to use, again, a modified peripheral scheduler that's now on the PCIe bus, and it receives messages from the cores. We had to obviously make a driver for the system to be able to receive these messages. We had to modify the real-time bridge to buffer not only the I/O data, but the interrupts as well. And then we created a compiler pass that basically implemented the described techniques. So we created a compiler pass for LLVM that did that. And so this is just a picture of the prototype. So you see here just 3 real-time bridges. These are FPGAs plugged in on the PCIe bus. So we actually built this type of system, and we evaluated as well. So This evaluation was done for a unicore system. So actually what we did is we took a quad-core system. We used 2 of the cores that had a shared cache for the non-real-time tasks for running like the user interface so we could interact with the system. We didn't use that during the experiment. And then for the other 2 cores, we turned off one of the cores. So then we had 1 core with an isolated cache that could then run these real-time tasks. We set the CPU frequency and memory bandwidth to be in line with parameters for embedded systems. We disabled the speculative hardware prefetcher, which, if you remember the previous talk, that was a big source of unpredictability. So there's a processor instruction you can do to turn that off. We changed the page size to be 4 megabytes, and that's basically to eliminate memory accesses due to the virtual memory system. And then to evaluate the compiler, what we really wanted to get at is how difficult is it to change or write applications that are prem compliant. So we have a large number of benchmarks that we did to check this. So I'm going to be describing 3 types of benchmarks in this talk. The first is a DES cipher benchmark. The reason I'll talk about that is it's very easy to change the input and output size for that benchmark, and you can see how that affects the execution time and the cache misses. We look at a JPEG benchmark. The reason I talk about that is that's a large collection of files. It's a much bigger benchmark, and as programmers, none of us really understood it fully, so you can see sort of what the process would be if you're going to an unknown code scenario to apply prem. And then we wanted to apply it to a larger group of benchmarks, so we looked at the automotive group of MeBench. So we did run all the benchmarks with multiple input sizes, but of course we're showing here just some of the representative measurements. And so in order to measure the sort of worst case, what we would do is when we're counting the number of cache misses, before we ran these tasks, we would manually invalidate the cache. So then you could see what the worst case number of cache misses would be, or at least something close to the worst case. So for the DES benchmark, you can see here that we can modify the input size, and then we have various parameters here. So these numbers are the number of cache misses that occur when you run the benchmarks. The non-prem method is completely unmodified. So if you take the benchmark and you run it by itself, you'll have this number of cache misses for the different input sides. For the prem method, we took the cipher function and turned it into a predictable interval. So we did prefetch and then execution. And so in the prefetch phase, we would experience most of the cache misses. And if you compare the number between the non-prem and the prem method, you see we do have some more cache misses due to the pessimism in the prefetching. But the number is pretty comparable, especially when you get higher up. During the execution phase, we have almost no cache misses. Now, the reason there's still some cache misses here is that it says 1, but actually that's an average over several runs. So sometimes we would see 0, sometimes we'd see 2 or 3. So the reason why we still have some cache misses is actually the cache replacement policy in the core. So if you have a random cache replacement policy, let's say, on your core, and you're doing this prefetching, while you're doing prefetching, you can evict memory that you've already prefetched. And then during the execution, you'll have to access this memory. So then you experience a cache miss. If you have a more real-time-ish cache replacement policy, if you have something like LRU, or even for pseudo-LRU, the tree-based one, there's some analysis that basically describes how much memory you can fetch before you start experiencing these self-evictions. So if you have that type of cache replacement policy, we could actually see 0 cache misses here. The last number is basically that's due to the size of the cache itself. So you can't prefetch arbitrarily large amounts of memory. You can only prefetch up to the size of your cache here. The key result here, though, is the predictability, which means that although these are the cache misses that occur when the tasks run in isolation, in the presence of I/O traffic, the execution phase here, its execution time will not change, whereas the non-prem method will have an increased worst-case execution time. For the JPEG benchmark, what we did is we took this JPEG, we ran it through, we took a sample code for JPEG, and we had some example images for encoding, and then we ran it through gprof, which basically told us that 80% of the application was being spent in one function called compressed data. So then that's the function we focused all our effort on in terms of making it predictable. So in the non-prem method, we noticed that the number of cache misses is comparable to the prefetch in the prem method. And actually the execution time is very similar as well. The same thing for this larger 8 megapixel image. the number of prefetch cache misses is slightly larger than the regular number of cache misses, but the timing still remains very similar. And again, we have some residual cache misses during the execution phase due to the random cache replacement policy. One thing you'll notice is that actually the time here is slightly smaller than the non-prem method. So you might wonder why that is. We'll come back to that in a few slides. The last benchmark we ran it on was the automotive program group of MeBench. So this consists of 6 benchmarks. 2 of them were not memory intensive at all. They were computation intensive. For those benchmarks, you don't need something like prem because those benchmarks basically don't access this shared resource. So for those benchmarks, you won't notice an increase in execution time due to I/O traffic or memory contention. The other 4 benchmarks are shown here. So 3 of them worked pretty well for prem, so the number of cache misses is comparable for the non-prem method, the unmodified way, and in the prefetch phase of the prem method. For the last benchmark, Susan Corner, we actually ended up prefetching much more data, and the execution time is correspondingly much bigger using prem. So the reason for that is in the Susan Corner benchmark, there was a variable output size. And so when you have this variable output size, what we ended up doing is prefetching the entire output buffer, whereas only part of the output buffer was actually used over the course of the execution. So I would argue, though, that this is probably not good for a real-time system because if you looked at the worst-case execution time of this task, you would have to look at the most pessimistic case where you use the entire output buffer instead of this one particular case that we measured. So, but it's good to know that there's what are the reasons why you wouldn't be able to use prem. One of them is if you have variable access sizes that you can't determine ahead of time. Another set of experiments we did was basically look at the effect of the worst case execution time of the task when it was run using this prem method and when it was run using a standard method. So you had noticed before that actually we were able to decrease the execution time of the tasks by doing this prefetching. You might wonder why that is. So to do this measurement, we created 2 synthetic tasks which accessed main memory. One of them accessed it in a linear fashion. One of them accessed it in a random fashion. And then we modified the memory references to control the amount of total cache stall time. So that would mean that these tasks would access a variable amount of memory. And then we compared 3 different scenarios. One is completely unmodified. How long does this task take to execute? What about if this task is what if there's I/O traffic running at the same time as this task? What's the execution time? And then if it's prem compliant, what's its execution time? And so in the prem compliant way, that doesn't matter whether you have or you don't have I/O traffic because if the I/O traffic is only scheduled during the execution phases, there's no memory access, so you won't see an increase in execution time. So for the random memory access case, you'll see a curve like this. So actually, the predictable method, the prem compliant way, has a lower execution time for all of the cache stall time percents. So that means that even when you compare it to the completely unmodified code, just by doing prem compliant without any I/O traffic, we can have a faster execution time. And actually, the reason for that is the behavior of the DRAM. So DRAM works much faster if you access memory in a linear fashion. So by doing prefetching, we're accessing the memory in a linear fashion, and then when it's accessed randomly later on, it's loaded from cache. And again, the predictable method is insensitive to I/O traffic, whereas the black line basically goes up to the red line in the case that I/O traffic is present. So there's a change in worst case execution time due to I/O traffic. For the sequential memory access case, what you have is now the predictable method is generally somewhere between the compatible method without I/O traffic and the compatible method with I/O traffic. And so this is again sort of the reason why the compatible method is generally faster than the prem method is, one, we're doing prefetching ahead of time, so we're inserting some extra code. But also, modern processors can do out-of-order execution. So that means even though they're waiting for one cache miss, they still might be able to execute some other execution that doesn't depend on the memory itself. So when we do prefetching, we don't have this property as well. So that's sort of why we're worse off than completely unmodified without I/O traffic. But if you compare the worst case, which is when I/O traffic is present, where the blue curve is still below the red curve as well. So you still have a gain from prem in the case of I/O traffic. So The last thing I want to talk about, which I have just one slide on, or 2 slides, is about scheduling in the system. So originally when we designed Prem, it was for a single core system in the case of I/O traffic. We're considering extending this to multi-core systems where you have basically statically partitioned real-time multi-core scheduling. So you have a set of tasks assigned to a processor, and they're executing on that task. So we developed an associated scheduling theory based on this notion of tasks that have predictable intervals where they access main memory at some parts and they just do execution at other parts. So the main idea for this type of scheduling is that we first schedule the most constrained resource in the system. So the most constrained resource in a multi-core system with I/O would be the memory access rather than the CPU computation. So we come up with a high-level TDMA schedule for when each core should access main memory. And then cores will only access main memory during their granted TDMA memory slot. The second rule that we do for scheduling is that you should treat your memory slot in a precious way. So that means that when your TDMA slot is granted, you should actually promote tasks that have memory phases pending over tasks that have execution phases pending. So this will cause some sort of bounded priority inversion in terms of the CPU schedule on the task. And then the third rule that we have is basically once you start a memory phase, you should let it run to completion before starting other memory phases. So again, the idea is you should finish as many memory phases as you can during your TDMA slot, so that when you don't have your TDMA memory slot granted, you can continue to execute the tasks. And so these are the scheduling rules. We've submitted a paper with the associated scheduling bounds that arises from these rules. Visually, the rules look something like this, where if you just do TDMA memory scheduling, which is this part here, and you have 3 jobs, the jobs can only access memory during their granted TDMA memory slots. So they may be stalled during these execution intervals. So here you have a response time of 15 time units if you just allow memory access during your TDMA memory slot. The TDMA memory slot, by the way, is the gray regions here. If you promote memory access to a higher priority when when you have your TDMA slot, you'll have this type of schedule where now this task is, let me see, instead of running here, you would normally run this execution phase, but since you're still in a TDMA memory slot, you actually run the memory phase for the second job. And now you have something more to execute here, you can lower your response time to 13. And with the last rule where you basically allow memory phases that have started to finish before starting other memory phases, we can further lower the response time here. So the difference between these two is basically this beginning part here where J2's memory phase is not interrupted because J1 arrives. So here we let it run to completion and we have something to run during the non-granted TDMA memory slot. And so now we lower the response time to 11 time units. So in conclusion, we basically took an experimental approach where we took real-time systems, we tried to run real-time tasks on them, we noticed what the problems were, and then we came up with solutions and we implemented them and tested them to run them on. So for I/O traffic, we transparently buffered them with our I/O management system. For memory traffic coming from the cores, we proposed modifying how the execution model of the system itself so that we can predict when memory access will occur from the cores, and that's the idea with Prem. And then once you have these two, you perform a high-level co-scheduling among the active components in the system to ensure that only one component accesses shared resources at once. So this means you don't have to rely on the low-level non-real-time arbiters. So the current work that we're doing is we're trying to automate this Prem memory clustering process. So I mentioned that was the hardest part, is basically looking at the task and figuring out what memory it can access during the predictable interval. Well, the way we did that is first we figured out, we used gprof to profile the code and figured out where most of the computation was done, and then we used tools like Valgrind to figure out which data structures were causing cache misses in that predictable interval. We think a lot of this can be automated, so we're working on doing that. We've only implemented Prem so far in a single core platform, although we have the schedulability that works for a multi-core one. So we're extending our implementation to the multi-core platform. Thank you.